Okay, so we're going to be doing lead code 1351, count negative numbers in a sorted matrix. So given an m by n matrix grid called grid, which is sorted in non-increasing order, in other words, in decreasing order, both row-wise and column-wise, and you're supposed to return the number of negative numbers in the grid, right? So here they ask you, can you find an O of n plus m solution? I think a better solution would be m log n. M log n would be better than an mn solution, m plus n solution, right? So row-wise, they are sorted in decreasing order, right? And column-wise, they're also sorted in decreasing order, right? For each column. Let's first start draw this so that you can see. So this is this is 4, 3, 2, negative 1, 3, 2, 1, negative 1, 1, 1, negative 1, negative 2, negative 1, negative 1, negative 2, negative 3. So you can see that it's sorted like this, right? In decreasing order. And at the same time, you can see that it's sorted like this in decreasing order, right? So the first way we can do this is by simply searching through the whole matrix, right, through every point, while counting the number of negative numbers. So let's do that. But that takes O of m by n, where m is the row length and n is the column length. So let's do that. Right? So we'll have row length is equal to length of grid, and then we'll have the col length, which is equal to length of grid at index 0, right? So for rows in range, row length, and for columns in range, col length, right? Here we need a counter for number of negative values, right? So we'll call it numnegs. Numnegs is equal to 0, right? And then here we say if grid at this row and at this column is less than 0, then we found a negative value. So numnegs is plus equals 1. And then here we simply return numnegs. Oh, rows calls. Okay, so voila, it works, right? But this is O of m by n because we're going through each and every single point in the matrix. So we can do it in O of log n time by we create a binary search method for each row, right? A binary search method for each row. So what we do is we take out each row, we go through the matrix taking out each row and returning how many negative numbers. So how would a binary search method for how the binary search method for this work. Right? So for our binary search, we will obviously have 2 pointers, I and j, right? But we want our pointers, for example, 4, 3, for the row 4, 3, 2, -1, right? We want our ith pointer at the end of this binary search, once it's exhausted, to be at this location. In other words, we want to exclude all values greater than or equal to 0. It's important to add the equal to 0, because if you just do greater than 0, then that means that you're telling I greater than 0, right? You're saying that j, because this j is supposed to be coming here, right? You're saying that j is supposed to exclude all the, because the reverse will be j is less than or equal to 0, right? So that means that j will stop at the position where you have all the negatives plus 0. 0 is not part of the negatives, right? You'd rather count 0 as part of the positives, right? So that's why it has to be I greater than or equal to 0, right? And at the end of this binary search, the negatives will be in this half, in this portion of the array. So you simply return the length, to find the number of negatives, the length of the array minus the position of I, right? Because I will be at the position j plus 1, right? So let's let's try it on a different row. So for example, the row, let's see, the row 3, 2, no, let's do this one. The row 1, 1, -1, -2. We want our I and j after the binary search. Our I should be at this position and our j should be at this position. This is the point at which they terminate, right? And you can see that the length of this array is 4. This is 0. This is the index 0, 1, 2, 3. When you subtract where I is, you get 2, which gives you 2, which is the number of negatives, right? The length of the array minus I will give us num_negs, right? So let's do it for another row so that you can see. This one is completely negative. So let's say the last one, -1, -1, -2, -3. 0, 1, 2, 3. Right? This is going to make sense when you look at the code. Our I will start here, our j will start here. Remember, our binary search is I, we exclude all, I greater than or equal to 0, else it will be j less than, greater than, so less than, you don't have to worry about this. So it will be j less than 0, but you don't have to worry about that. So anyways, we want our binary search after it's exhausted. Our I will actually be in this position, and our j will be in this position. So our I will be at 4. So what's the length of our array? The length of our array is 4 minus, we won't consider the I in this case because it will have gone off. So I will be 0 in this case. And then our answer will be 4. Right? And the reason we don't consider it is because our I will have gone off. It will be actually at index 0. Our I will remain at index 0 because we'll never, our J, sorry, with this, what will happen is our I will start here, and then our J is the one that will move all the way to this side. So our J will be at index -1. So here our I will be 0, which will be 4. Sorry about that. Our I will remain at this position because it's already with a value greater than or equal to 0. Right? So let's code it out. Right? So we have, for this, how we're going to get the rows, right, is going to be actually very simple because of Python, right? So we iterate through the grid, through the matrix, grab each row and binary search it. We binary search it using a function. This function returns the number of negs, negative numbers at that row. We add the negative numbers to an accumulator. So here we'll have numnegs, the infamous numnegs, and then here we'll have for row in grid. Simple as that in Python. Then we'll say numnegs plus equals, we'll call it find negs function, and it will take the row. Right? Then after we're done here, we simply return numnegs. Right? So we create the function to binary search each row. We're going to call def find negs. It takes a row. We'll call it matrix row. Right? So we create 2 pointers. I is equal to 0, j is equal to length of matrix row -1 because we started at 0. Then we binary search. Binary search in this case is about exclusion. So while I is less than or equal to j, we calculate our mid, which will be I plus j divided by 2. Some people prefer to do it like I plus j minus I divided by 2, right? And then we check. We check if we exclude it on the left or on the right. So if matrix row at mid is greater than or equal to 0, then we want to put it to the left side of our I pointer. So I is equal to mid plus 1. Else, this means matrix row at mid is greater than 0. No, is less than 0. So we want it to be ahead of our j pointer, right? So our j is equal to mid minus 1. Then once we are out of this while loop, we simply return length of matrix row. We simply return we simply return length of matrix row minus I. Or you could make it j plus 1. Right, so let's run this code. Voila. Oh, that's such a good feeling when it runs well first time. Run it again. Yeah, we have a faster run time. So previously we're doing this because we want I to be to the right side of all values greater than 0. So all positives, right? Greater than or equal to 0. And we want j to be to the left side of all that are negative, right? So that's why we do that. And then after the exhaustive binary search, this is what we do. So previously, when I was trying to do this, I tried j plus 1. Let's see if it runs. Voila. It works as well. So I think the mistake I was doing, I think when you do it like this, it doesn't work. So you need to, yeah, that was the issue. You need to put it in brackets. So you can either do j plus 1 or I. Voila, voila, voila. Let's run it again to get a higher runtime. Perfect. So this is an O of m, which is the number of rows, log n, number of columns. Right? And this is actually the fastest